All right, welcome to the morning live stream. Right now, what I would like to do is dive a bit into the units. So the unit is basically an encoder decoder, just like the autoencoder that I've been working on with the additional extension of the skip connections between the layers. Basically here the decoder works with the encoder's output on the same level, and the encoder's output is concatenated to the decoder's input. This stabilizes learning. However, it makes it more difficult to detach either the decoder or the encoder from the other. So this is used in stable diffusion and lots of image and all kinds of generative models. And right now I'm more interested in generating a cool reconstruction from the input without skip connections. So in that way these two can be split, and then I would be able to use just the encoder as a kind of tokenizer, since we're talking about vector quantized autoencoders in my case. So if that doesn't really work out, then I will start working on the units, and I will cover it a bit later anyway. So also a bit later I will dive deeper into diffusion transformers from Facebook. But for today I have this research publication. It uses a dual codebook, as you can see, for enhanced image reconstruction, and this doesn't have skip connections as far as I know. So the encoder outputs a latent grid of latent vectors, splits it into two. One half, as I understand, is processed with a transformer for global feature extraction. The other isn't. Here is the transformer and the global codebook, and this extracts local features. So the loss function is different for each. Then it's concatenated back into a latent and fed into the generator or decoder. So the total loss is E global, E local, and the total loss is, so there's a GAN here. Even before this, there's a hierarchical. This is a 2022 paper. Let it load. I haven't actually seen this research paper yet. It uses multiple codebooks, more than 2. And I came across a simple trick that I actually want to implement right now. So I have this autoencoder already quantized into a codebook with residual down and up sampling blocks and a simple transformer multiple blocks actually. So how this works is there's an encoder with skip connections, but only to the next layer. Takes an input image, there's a convolutional part. Just because I'm working with small images, there are only a few layers. Here the skip connections, basically just convolutional projection with a kernel size of 1 and stride 2 to it downsamples to the next layer. And with positional embedding, I create a grid from -1 to 1 for both X and Y and attach it as a channel to an RGB image. 2 channels actually, so it becomes a 5-channel input. The decoder. Oh yeah, so after the convolutions, I feed the latents to a transformer, sequence of transformers basically. Then quantize it, feed it to another sequence of transformers in the decoder, and then conv transpose upsampling generator sequence. Now the codebook is used pretty much, so perplexity is high because I added a refresh codebook feature. I'm keeping track of the generated continuous latents and also the codebook usage during training. And once in a while, every n epochs, I find the dead codes, the codes that haven't been used for the last n steps, find the replacements from, and this is I think an important bit, I log the continuous latents because I randomly sample them when replacing the dead codes. So the replacements, so the new codes that replace the dead codes are actually randomly sampled previous outputs of the encoder. So this way the codebook is utilized quickly in a large percent, and I arrived with a pretty good reconstructed image quality, but it's still not like the original. I only use an L1 loss. I don't want to use VGG based perceptual loss because I just don't want to rely on an external model to improve the performance of my own model. basically in that case VGG it would be training my model. So for me at this stage it kind of feels like cheating, and so I would like to arrive with as good of a reconstruction as it's possible without skip connections. And right now I'm going to train two versions of this model on two GPUs. So once I would like, yep, so this is going to be experiment number 1 and experiment number 2. And in both, I'm going to disable the transformers, so it becomes a standard VQVAE. So set the layers to 0 here and here as well. And the only thing I want to change is that in the second experiment, I remove the position embeddings. And in that way, input will be just a 3-channel something. I want it to train for 250 epochs. But let's find the device declaration. So this should be CUDA 1 for the second GPU. Rerun. This should be CUDA 0. And let's run the training. So the codebook size is, I think, 1024, yes. Dimensions are 512. So as you can see, it replaces the dead codes. However, I only run the code replacement in the first half of the training, because by that time they should get pretty close to where they should be, and I don't want to make quick jumps at later stages, so I let the network learn from those codes. Let me check the GPU utilization. So that's almost 5 gigabytes. And interestingly, this is just 2.5. The same number of model parameters. Auto-casting whatever I can to get 16-bit precision, and using the gradient scaler Okay, so while this is training, I'm going to close my window because there are some guys working on the roof at the neighbor, and it would disturb the live. So once this finishes, we will compare whether, in this case, position embedding as two new separate channels make any difference. So GPU 2 is on a slower PCI slot. I'm not sure if that's the reason that it trains slower. There are probably other factors involved as well. So both finished. Let's check the position embedding. So this after 250 epochs with position embedding. I don't really expect much of a difference, to be honest. I mean, the first one does look better. So there is a slight difference. And I use a manual seed for both. Still doesn't guarantee complete determinism. But let's put this side by side. This is not a conclusive test at all. But I will use it as one. It's at least an indication. So the hair here is better here. As you can see, it kind of makes it look like that his hair was this long, but actually this lower part, it might be just, it looks like it's just shadow. And here we can see a kind of blurry ear emerging from the background. Still not there, but with a bit more training maybe. But overall, the reconstruction quality, it's how it is, blurry. And in order to make that better, I would like to use multiple code books. Now let's just keep experiment 1 as it is. So we know this was the better model with position embedding, and train the second experiment. Now just let me revert the embedding code. So use this line and add 2 more channels. And let's just see if we add another code book, how that changes the reconstruction quality, if at all. How do we add another code book? It's here. I already added the line, but it's not actually used. Only VQ1 is used. So a way to make this, let's actually use the same parameters for simplicity. And we have ZE, the continuous latent from our encoder. And we have this ZQ straight through, which is the quantized result. So this is actually a code from the code book. And they have a difference. Let's call this ZDiff, because the encoder outputs some vector, and then you quantize it with a jump. So this is the codebook code closest to, so from the whole codebook, this vector is the closest to the actual output of the encoder, and you make this jump. Because you say that we treat this code like it was the actual output from the encoder. But between these two vectors there is a difference. And that is kind of information lost. So we take this difference vector and quantize it in another codebook. There will be another difference between the difference vector and another quantized code. So we could also take that. It will be a smaller difference. We could also take that and feed it into another codebook. And this way we would be approximating with smaller and smaller steps. Let's see if this theory holds any validity. So zdiff is ze minus zqst. And this is, by the way, in the shape of batch, and I believe that DHW, the encoder Z-shape output is this. So this is actually B times H times W number of vectors. And as that, I would rather reorganize them to be BHWD and then subtract and convert back. So let's do that. Let's put it into another function so we can have less variable names. So calc latent diff vector zqst. Let's just call it zq. This will be self.calc latent diff vector zq straight through. And use the other codebook. Whoa. VQ2 with zdiff, and this will be zdiff q straight through. This will be VQ loss. Let's just call these 2 as in level 2. So ZQST2, because if we add another one, that would be level 3. And this is, it would be zdiff1. For now, let's leave it at zdiff. So we quantize it. And the total loss we need to add the loss to the total VQ loss. And the decoder should work with ZQST plus ZQST2. We can return perplexity too. However, codebook updates are running for VQ1 only, and it's the model. Where is my model? This is the model, yeah, sure. In this case, we would also need to keep track of the diff vectors. Update VQ2 with those. So this permutes ZE from the encoder, and this should be in the same shape as ZE, so we can work with Z diffs. This is actually not the dead code replacement, it's just logging. So let's do it the same way. And separate our code a little bit. So this is level 1. This is level 2. That's the total loss calculation. We can move it here before we return it. Logically, it's a better place. And decoding. And of course, this becomes ZDiff. It's basically the same, but let's work with the actual vector. And we have logged ZE2. You're going to copy it there. So log ZE2 stores these diff vectors. And I initially implemented it with random sampling, but as I see, I reverted it back for now in a simpler way. So because we have a pretty big batch size, and there's the assertion here that the codebook size must be smaller, and we are working with 4x4 patches. So in one batch of samples, there will be 16 times the batch size, which is len ZE, and there could be a much more proper calculation for this, but for the sake of simplicity, I just put this assertion here, and most of the times for this faces data set, and in this example, this will just work. So just by running one batch, I sampled that latest batch for the latents and log it here. And when refreshing the codebook, there's a random sampling from those new codes. So these are the stored latents from the last batch. So we are randomly sampling from the last batch of latents as replacements for the dead codes, and the dead codes are defined, so those are codes used less than 20 times in the last 5 epochs. And then when we refresh the codebook, of course, the codebook use will be zeroed out. And this is just, so these are the distances for each input latent. So this is squashed to batch and the patch size, k dimensions. The codes store the indexes to the closest latent vectors in the codebook. So we do a bin count, calculate, count each code, how many times it's used in this, and update the codebook use, which is an array of k. So this maps the codebook index to the count in the last period where we didn't refresh the codebook. In this case, 5 epochs, because in the training code I've set it to 5. So where were we? The level 2. It also has a perplexity. We add these together and the decoder decodes that. All we need to do is now calculate the latent diff vector. So this is in this shape. And well, I have a small issue because I just used D. I reserve this variable name D for the device. I'd like to rename this to dev so we don't confuse it with this latent dim. So let's just find all the uses to D. Replace it with to dev. Also, in any case, if I have, yeah, I do. This isn't actually a good way to do this. Or on second thought, it is enough. I was thinking that when you move it to CUDA or you move the model back and from the CPU to CUDA and back, then this would not change. But however, this is declared in the forward pass, so wherever the model is, the device here will be the same, and these are just temporary variables concatenated to the input. So this will work just fine. And now I want to do the same for this one. To D, to dev. So now, without confusion or naming conflicts, we can work with D. So this is the shape we have for ZE. and we take ZE, permute it, so batch stays at the same dimension, and then we need the height, the width, and the last one will be D. Make it a contiguous memory space. This one reorganizes the memory, and now we can view it as -1 will be BHW inferred and D. Let's do the same for ZQ. Now ZDiff becomes ZQ minus ZE. I'm not entirely sure if this only subtracts from the last dimension and treats the first dim as the batch size, so I will have to verify. And when you're unsure, just create small examples. So A is a torch.tensor in the size. So for example, we have 1, 1, 1 and 2, 2, 2. Batch size is 2, and this is 3 with 3 length vectors. B, same batch size, and subtract 0, 1, 0, 2, and that, and print A minus B. Yes. I can't undo. I wanted to play around a bit more. Let's quickly rewrite it. So it's 1, 1, 1, 2, 2, 2. B. And print A, B. Print them in new lines. Now let's permute A. So we only have 2 dimensions. This be A2. Print A2. And let's view. Well, we cannot really do much with that here because it's only 2-dimensional tensor. So A2, this one, is a transposed. It's basically the transpose of it. Let's make B 3-dimensional tensor. This becomes 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6. So this now has a shape of, call it batch D, and the actual shape is 3, 2, 3. So I'm gonna reorder printing. We work with A there. B2, B2. So let's permute this. So these are the dimension indexes as they are by default. Let's instead assume that D is here, and this is, call it HW. It won't work because this number is not even, but let's just assume that it's that. So we have the batch at the same position, but now we move HW here and D to the last dimension. So in this case, B2 will become this. So the inners will contain 5, 6. All right. Play over. It's actually, my original question would be, do we even need these permutations? So let's rerun it. And make a C torch.once like B, and print B minus C. I mean, the values should be this. This becomes C, and we print B2 minus C2. Because in the end, these are just numbers shaped in a different way. So, okay, let's remove this. Remove everything else. So basically the values are the same. I don't need to permute here anything, because for a single subtraction it should just work as is, which means we don't need this separate function. I can just do this. I'm not removing it just yet. Here, this is ZQST. Okay, so 2 code books. Let's rerun everything. And run the training. We can't. Yes, because I have perp2 now here as well. And I would like to log those two, perps2, perps2, and perp2, average perp2, perps2, this time I'm not going to do the same for evaluation. It's kind of the same anyway. This will become average perp2. Yeah. And the VQ loss. Training is running. Now meanwhile, let's make use of the other GPU and run experiment 2.5, another branch. Just I'm making sure that I saved everything. So experiment 2.5. And in this one, actually I should branch off from a known result. So we know this works like that, so I'm gonna branch off from experiment 1 actually, sorry. And then if experiment 2 yields better results, then branch off from that. It would actually be nice to create a framework or find a framework, I'm sure it exists, where you can store the differences and run branches of these experiments. As you change the hyperparameters, branch off from each and store which one worked how. So this is running on GPU 2. This will run on GPU 1. I want to measure how much the reconstruction quality changes if I add 7% noise. I'm not sure how small these numbers are in trperp2. Maybe I could upscale those diff vectors when performing the quantization in VQ2, and then downscale it when I add them together. I will try that in the next training. Scale them up by 10, for example. Or another way that I saw some people do this is by, I think, normalizing the latents. When calculating the distance, so normalize ZE, the encoder output, and normalize the codebook vectors and calculate a cosine distance by taking the dot product of both. So that actually gives the cosine of the angle between them. Almost finished. There are many code books, DAT codes. So this is utilized a bit better. This one is just at around 40%. Let's try. And compare with experiment 1. I'm not sure if it's better or worse, to be honest. Now it's the time maybe to start using some algorithmic image quality comparison. It kind of looks somewhat better because of the lower shadows here are more pronounced. So I'm going to make this scalable. Just save the results. So this is with 2 code books. Is there no text tool here? Okay, so 1 code book. 2 code books. No scale. And this is the dual code book. So we're not using transformers in our examples. So let's check what we are. Let's check if what we are doing is actually something like the hierarchical. Well, it's not the HR VQVAE that we are doing, but 2CB no scale. So I want to try and spend just a little while on and levels, say, and integer. Self.vqs will be a quantizer for in range and levels. Let's remove this. For VQ in self.use update all. This should be zeros, but and levels times that, and let's store and levels actually need to enumerate to get the index. So log ze at I and for I in range, so for each level, and if I equals 0, so the first level we get the ZE from the encoder. else ZE will be prev ZQST is none. We will need to set this one at the end of the, let me just indent this. And we could do this instead. So here we call the actual current VQ, and the prev will become this. Here we need to calculate the ZD from the prev Z minus ZE, and we also need to store, in this case, the prev ZE, which is initially none. And we set that at the end of the iteration as ZE. Now, the rest we don't need, except we will have a final quantized vector. Final ZQ is none. And if I equals actually we could set this to 0, but I don't want to assume the shape of this here, so let it be none for first, and that will be this, otherwise we add it. Now this one can be, let's make it 3 layers or 5 layers. I won't anymore return this. So the VQ loss, prev ZE is not used. Why? Because we need to use it here. And that's the final ZQ. And the final loss is none. So if I is 0, final loss will become the VQ loss, and otherwise we add it. We don't actually need this here because we have self.d. Now for the logged ZE update, I'm not anymore saying, let's use the first dimension and log ZE because it has n levels. You can just copy it as is. But What can I do? It's actual memory. So asking quick technical help from the AI. So instead of using data, it appears I can just address it with I and use copy. Okay, and we have 5 code books. Perplexity. I would just take the mean. Also, let's scale this up. So the scale at first is 1. It's 1. We can torch dot use a simple exponent maybe, or torch.pov. That's the input. That's not really what I want. So torch dot full. What's full like? The fill value. That's what I want. Okay. So the input, we need the shape of the prev ZE. Let it be 10. This will be our base. No, scratch that. I'll just multiply it by 10 for each level. So this times 10, because for each layer this will accumulate. So that's the ZE. Perform the quantization. Arrive at the ZQST. Here, divide by 10. And the loss should also be divided by 10. And let's just I should return an array of perplexities. Perps dot push append perplexity. I will return perps. This will change quite a bit. So this becomes perps and torch. Take the mean of all levels. Perps dot mean. Also here we change it to an array. Now we don't have perps 2. Just perps. And it's an array. So here I need to detach it. Or instead, to see deeper into what's going on, use array of arrays and so perps. I would need to reshape it or calculate the mean on dimension 1. Then this will be a torch.tensor. Let's try running everything, and the default is 5 levels, no transformers still. And this is because I need to have a module list here, so it will move it to the same device. Let's see if we have any other errors. Yeah, we don't need that anyway, it's the same. Image tokenizer, yeah, some leftover code. this one. It doesn't. Sure, because we don't store it, so plug D becomes D. Okay. This just won't work. The training loss becomes so huge. What are these perplexed? So I would like to see 5-element array here, but instead this has a length of 21. Let's deal with the huge loss first. So I scale these up. Well, ZE doesn't make much more sense here. So what's returned is in this order, and that looks fine, but the final So my first question is why the loss is so high. when I'm adding only .1 of it. So instead of scaling up by 10, I could just normalize this. Maybe not, because then how do I convert it back to the final ZQ? So question, why is the loss so high? Also, we have an issue here, but that doesn't really matter. The training loss becomes extremely huge. So to debug this, I will just run a single epoch, or yeah, just try running 5 epochs and print some stuff. So let's print level I, VQ loss. I also need to scale this back, because this returns the scaled up version, and scale this down too, but in that case let's try this one. So L for the VQ loss, it grows layer by layer. Yep. I don't like divisions, especially this many times. One epoch is fine. The loss is still growing. Uh, ten times layer by layer. What if I don't scale up anything? Because I would have expected, since the vector becomes smaller and smaller because the difference is smaller and smaller, that I would need to scale it up a bit. But this destabilizes the network entirely. And of course, this is initted the same way for all levels. Well, anyway, let's try to train this further without scaling. Ah, come on, I didn't rerun the previous blocks. Restart our kernel. Rerun everything. No, I guess I'm still printing and that's just not going to work. Let's see if we can even get convergence. It is converging. But the deeper we go, the more dead codes there are. Less and less. Well, this is training. We have a noise, 7% noise that I already ran. So we can compare the reconstruction with the one that doesn't use 7% noise. And it's worse. It's a more general understanding, I guess, and a more, well, this person looks like a more general person than this one. He is more specific. He has more specific characteristics to himself than him. So, okay, let's save that. Not dealing with noise anymore. And the log. Still many dead codes. At least here. Here it's fine. I'm not sure what's wrong with the perplexity, is something with the mean. I'm not debugging that now. Just check the reconstruction quality when it finishes. So this is just a try of that idea, but the actual thing is this, the dual code book research. So that's how we can get this to work, what it does. So I mentioned I needed a better algorithmic way to compare two images, and the VID is apparently that. So I'm going to utilize it in the code book. So apparently the VID distance can be calculated from torch matrix image.vid import Frechet inception distance, and the VID is, well, that feature. Let's use the default value to device, and we can show it. Let's move it. Frechet inception distance. Need to call VID update the real image is image dot squeeze at 0 and to device, and y hat is just y hat. Call it fit score fit.compute.item. Yep. Well, let's install torch matrix image. Okay. Do I need to restart my kernel? Maybe. So that's just that. This doesn't really do much. Two 50 epochs, 0.32. I mean, it's is it converging? 150, it's already at, actually, it started to diverge. Let's just bump it up a little bit. So far it's converging. We will see. It didn't explode like before. It's at 0.6. That's not so much better, eh? Let's leave this to train. So this is not the decoder, this is a discriminator. Now, where did it go? Come on. So basically they generate a latent vector, just split it in half. And process the first half with a 6-layer transformer, and the other just goes into a code book. Well, I could see, and it's in the previous live streams, that transformers do help with precision, and it's less blurry, but a huge quality jump is achieved here with the GAN. G is the decoder, and D is the discriminator. Adaptive weight lambda. So I need to implement a discriminator too, and introduce the adaptive weight lambda. So what's E? Is that the code book? E refers to the encoder. I'm not sure what this is. So if this is the encoder, and then what's encoder global and encoder local, or is this the concatenation? but then it says the global and local code books comprised in are defined, so the code books are defined as. So is this the code book? Is this the encoder? What's this operation here? Concat, or I guess it's just addition. So what's the small x? What's the large x? It's the loss of the global and the local. So that's the loss. It's just added together. Okay, so this finished at 89, so it completely diverged. Select all these, this. Yep. So at 95, it achieved its minimum loss and then went up, and now it's also going down again. I could train it for another 100 epochs to see if it's just a. Let's make it 50. No need to refresh the code book anymore. This won't yield anything better. So the conclusion that using multiple code books this way failed. And instead of the hierarchical, next I'm implementing this using a transformer and a discriminator. And when that's done, I'm going to make a 90-minute or so video about vector quantized variational autoencoders and Part 2 will include the implementation of this dual code book VQ.